Okay, I want to thank the organizers for this opportunity to present this work. So, as we all know, quantization of strings in ADS 5 cross S5 is a very hard problem, so it's natural to look for simple settings where we can have some understanding. And it's natural to consider the propagation of strings in subsectors of the ADS space. In particular, when we study strings in R cross S3, the equations describe the motion of the strings are equivalent to the equations for the Faddeev-Reshetikhin model, which is an SU2 principal chiral model. This model has been quantized in the mid-60s by using the inverse scattering method, and more recently, motivated by string theory, Close and Zarembo found the two-particle asymmetrics using conventional field theoretical methods. So we became interested in this problem, and we tried to find the two-particle asymmetrics just by diagonalizing the Hamiltonian. That was supposed to be a trivial problem, but we couldn't find any solution. So I will show you why, and I will explain how we finally got the two-particle asymmetrics. And in the process of understanding why it is not diagonalizable, because Hamiltonian is not diagonalizable, we naturally asked the question of what is the most general Hamiltonian with quartic interactions which can be diagonalized in that framework. And again, to our surprise, we found that Hamiltonian, but it was not Hermitian. Even though it's not Hermitian, it is asymmetric, is unitary. That will be the other main topic of this talk. So this work was done with Ashok Das from Rochester University and Arsin Melikian from São Paulo University. So just as a motivation, I will remind you how to get the Faddeev-Reshetikhin equations from strings propagating in R cross S3. So we start with a string action in ADS 5 cross S5. We can use these embedding coordinates, the x coordinates for the ADS 5 and the y coordinates for the S5, and we just keep the time coordinate in ADS 5 and set it y5 and y6 equals to 0 in the S5 sector. We also have to take into account the Virasoro constraints. And since it is a chiral principal model, we can explore the standard map of the sphere S3 into SU2. And with this SU2 matrix, we define in the standard way the SU2 current. And the equations of motion for this string is just the current conservation equation. We also get that the Lambertian of the time is equals to 0. So when we rewrite the Virasoro constraints in terms of this current, it has this form here. These plus and minus are just the light cone components of the SU2 current. We also fix the gauge, the temporal gauge, proportional with a parameter kappa, so that the Virasoro constraints tells me that J square is just a constant. Okay, at this stage, it's very convenient to change variables. Since this current is a 2x2 matrix, I can expand it in terms of the Pauli matrices. So instead of taking J as my variables, I take this two vectors, S plus and S minus, as the variables now. In terms of these two vectors, the two Virasoro constraints just tell me that these vectors have unit norm, and the equations of motion, the current conservation now turns into this form, which are the Faddeev-Reshetikhin equations for the SU2 principal chiral model. Okay, the next step is to find an Hamiltonian from which these equations of motion can be derived. This has a standard solution. Since the equations of motion are of first order, we need two Vesuvian terms to have the kinetic terms, and the interaction terms are just the coupling of S plus and S minus. Now this action is not very good for quantization, so we change variables again to get the canonical kinetic term, and also to recall that these S plus and S minus are constrained. They are unit vectors. So when we do this transformation, this change of variables, we also take into account the constraints. So these two fields, these two complex fields, phi plus and phi minus, are no longer constrained. The constraint has already been taken into account. So we get this action, which has a nice kinetic term, but has an awful interaction term with the square root. We can still simplify this action. We can expand the square root and rewrite it in a more economical way. Okay, we can take advantage of the fact that this is a first order action and rewrite it in a way which looks like a Dirac action plus a potential. Okay? So we combine phi plus and phi minus into a column matrix, and even though it looks like a Dirac action, these phi's they are bosonic coordinates. And another important point when you look at these actions is that it has been written in a form that suggests that it is Lorentz invariant, but it isn't. You see that the D0 and the D1 have different formulas, and they explicitly break the Lorentz invariance. We also introduced the mass parameters and the coupling constant, even though we have just one parameter kappa, just for convenience. This was the starting point for Close and Zarembo to derive the two particle asymmetrics. They just use the usual Feynman rules. The only point that has to be taken into account is that it's not a Lorentz invariant action, so you have to take it the retarded propagator. Now, what we did was to diagonalize the Hamiltonian from this action. So the Hamiltonian is written here, and we postulated the usual commutation relations, and we choose the Falsi vacuum as usual in such case. So the two particle states are built in the usual way. We have the two creation operators. We have the wave function, which depends on the x coordinates and the momenta k1 and k2. The wave function is symmetric under the interchange of x1 and x2 and alpha and beta. Now, we can now look into the free theory. Now, since the kinetic term is Dirac-like, has a Dirac-like form, we can use the Dirac machinery. We can just have the equivalents of the U and V spinors, which are solutions of the free Dirac equation. So here are the solutions in terms of the rapidity. And we can look for the eigenfunctions of the momentum, which have eigenvalues k1 plus k2, and the eigenfunctions of the Hamiltonian, which have the value square root of m squared plus k1 squared plus square root of m squared plus k2 squared. Of course, the solutions are just plane waves, as expected. If I take the positive sector, I have to take, I have to use this U column matrices, and I combine the two independent solutions in this way, so that chi plus is symmetric under the interchange of x1 and x2 and alpha and beta, and chi minus is the antisymmetric combination. Of course, for the free theory, the solution is just chi plus, and the answer for the interacting theory can only have this form. It must be proportional to chi minus, and since this is antisymmetric, I must multiply by something which is antisymmetric as well. So in the only possibility is to have this epsilon of chi1 minus chi2. And lambda is just a factor, a momentum-dependent factor, which has to be determined. In this way, the two-particle asymmetric is just 1 minus lambda over 1 plus lambda. So, as I said in the beginning, this is just a simple problem. We have to write the Schrödinger equation for this ansatz, and there is no solution. Of course, we could say that this is not the most general ansatz. We could think in other possibilities. For instance, we can look into the Hamiltonian interaction applied to the two-particle state, and since it has a contact interaction, the interaction is just a delta function. We could solve the problem just requiring that before the two particles interact, I have plane waves. I have also plane waves after the two particles interact, and I have to take into account this discontinuity. I have to match this discontinuity. Also, this doesn't work. So, trying to understand what is going on, we saw that the guilt guy is this term which violates the Lorentz invariance. If we throw away this term in red, the interaction Hamiltonian is just the Hamiltonian for the massive Turing model, and in that case, I can easily find the solution. The solution is just the asymmetric is for the massive Turing model as usual. So this is the term which doesn't allow a solution for the Schrödinger equation. What it is doing here is mixing states of positive and negative energy. So what we did was just then, once we recognized the problem, we just have to multiply to take the inner product of the Schrödinger equation with positive energy states. Once that is done, we can find this value for lambda, which reproduces. This value for lambda, which reproduces the Faddeev-Reshetikhin model. So if you have an Hamiltonian which is diagonalizable, that always leads to an asymmetric. But if you know that the asymmetric does exist, it doesn't mean that automatically that the Hamiltonian is diagonalizable. So in this process, we asked what is the most general quartic Hamiltonian which can be diagonalized. And the answer is simple. It has only two terms. It has only these two terms. The first term, this first term is just the term which corresponds to the Turing model. And the second term is a term which also violates Lorentz invariance. Even though it violates Lorentz invariance, we can diagonalize the Hamiltonian. This is the asymmetric. What's interesting about this asymmetric is that when alpha is equal to minus beta, we get the same asymmetric as the Faddeev-Reshetikhin model, even though this is not the Hamiltonian of the Faddeev-Reshetikhin model. Now there is a problem here, because when you look very carefully at the hermiticity properties of this Hamiltonian, you notice that phi bar, gamma 0, gamma 1, phi dagger is minus itself, while phi bar, gamma 1, phi dagger is Hermitian. So there is a term in this sum here which is not Hermitian. So for this asymmetric is to be unitary, we need that alpha and beta is real. But if beta is real, this piece of the Hamiltonian is not Hermitian. So we have an example of a non-Hermitian Hamiltonian which has an unitary asymmetrics. Now this is not so surprising, because there are many quantum mechanical systems which have non-Hermitian Hamiltonians and have unitary asymmetrics and real eigenvalues for the Hamiltonian. Usually these cases have Hamiltonians which are PT symmetric. And there is a nice review, a recent review on this subject by Bender. So it's, what we did was just to check if our model was, had PT symmetry. We know that we can define the PT symmetry as in analogous way as it's done for the Dirac case, just take into account that our components of this phi are scalar fields, and our Hamiltonian is PT symmetric if alpha and beta are both real. So this is maybe the first example of a integrable model which has an Hamiltonian which is not Hermitian, is PT symmetric, and has real values for the energy. So to conclude, the asymmetrics for the Faddeev-Reshetikhin model can be obtained by the inverse scattering method, as in the original work, or by a field theoretical calculation done by Close and Zarembo. Its Hamiltonian is not diagonalizable because there is a potential term that breaks the Lorentz invariance. What we did was just take the matrix elements between the states to compute the asymmetrics. In the process, we found the most general quartic potential, which leads to a diagonalizable Hamiltonian. And we found that is, in general, it's not Hermitian, it is PT symmetric, and it has unitary asymmetrics. Okay, thank you. No, it's not PCT invariant. No, just for I had to approximate the action to fourth order. So I just looked into the two, yes, the two particle asymmetrics for the truncated theory. No, it's bosons. It's scalar fields.
Okay, it's not
Yeah.